In this lecture, we're going to talk about, I guess we're not really going to talk about anything new. We're going to go through and practice some heterolysis and homolysis questions or problems, I guess. And so my approach to this is to just kind of throw some molecules up in front of us and then say, hey, what do the arrows look like? Provide the curly arrows and provide the products for the following events. So let's say that we have this and we have heterolysis, homolysis, heterolysis, heterolysis, homolysis, and I'm going to point at a bond to break. As the molecules get more complicated, I think that's helpful. And let's just do one more. Where we have heterolysis, and I'm going to show the bond I want to break is right here. Okay, so what we're going to try to do is draw the arrows. I'll change my pen to green, and this is going to be the stuff that we add. I think I forgot a few formal charges, excuse me. Okay, don't have anything that's negatively charged. I think that's okay. Yeah, negatively charged things usually make bonds. They usually don't. Well, no, that's not true. Well, we'll go with this. We'll go with this for now. Let's not complicate our lives too much. Okay, so heterolysis. We have two bonds present in the first molecule. They are sort of the same. That is, if we do something to the left, we could do the exact same thing to the right and get the exact same outcome. So I'm just going to pick one of the bonds. I'm going to start at the bond and move to the atom. I think I'm going to go and push the electrons. I'm going to take them and push them over from the bond to the more electronegative oxygen atom. That's going to give rise to these two species. The bond has been ruptured. The bond has been broken. If the electrons are not shared, then the atoms can start to float away from each other in space. Now what's happened is the oxygen has picked up another lone pair of electrons. It actually originally started with two. You could just draw the two new electrons as one lone pair and then show a negative charge, because you remember that the thing that accepts the electrons always go towards the arrowhead, and the thing that accepts the electrons reduces its charge by 1, whereas the thing that has lost the electrons has increased its charge by 1. However, you could get there also with formal charge calculation. So the oxygen, which is a group 6 element, now has 1 bond and 6 unshared electrons. So 6 minus 1 minus 6 is equal to -1. If you want me to do that, I could do formal charge is equal to 6 minus 1 minus 6 equals -1. And hydrogen without anything attached to it is just a proton, and a proton is a positively charged subatomic particle. Okay, in the next example, we're going to go through homolysis. So we're going to rupture the bond. I'm going to zoom in. I'm going to rupture the bond so that the electrons move to each side of the arrow. Excuse me. So the electrons that are shared move to each of the atoms, one on the left side, one on the right side, to give us something that looks like this. When the bond breaks, the atoms can float away from each other, each as free radicals that are neutral, because we don't increase or decrease the charge of an element. It doesn't change when we do a homolysis reaction. Please note that you could draw the arrows above or below, whatever is most comfortable. Just make sure that I can tell that they're a fish hook. If you need to draw a full-headed arrow and erase it, just make sure you erase it and make sure it's clear to me that it's a fishhook arrow. Okay, and the next one's heterolysis. Many of these are heterolysis reactions. I'm going to push the electrons over to the oxygen atom because when I do that, I neutralize the oxygen in the center because it's picked up a lone pair of electrons and its charge is decreasing by 1 as a result. Now, when we decrease a positively charged species by 1, we get a neutral charged element, and in this case, a neutral overall charge on the water molecule, but the overall charge of the product still needs to be +1. So we're going to have a formal charge of +1 on the subatomic particle. Please note you could move the electrons in either direction. You could move the electrons over to the hydrogen. It's a tough reaction to pull off, and I have a hard time drawing it. But if you did, if you push the electrons in a heterolysis reaction to the hydrogen element, notice that all the bonds again are the same. You know, if you push, if instead of picking the lower right hydrogen, if I pick the upper right hydrogen, I would get water and H+ again for me. But if you push them in the opposite direction, you would just get different charges. You'd have a plus charge on the, you'd have a +2 charge on the oxygen atom and then a -1 charge on the hydrogen element. Okay, but I still am a big fan. If I'm doing this, I'm going to try to do it so it's chemically correct. I'm going to push the electrons from the electropositive, from being shared between an electronegative nitrogen and an electropositive hydrogen to being on the electronegative nitrogen. That gives me a neutral nitrogen element, and we could prove that as 5 minus 3 minus 2 equals 0 plus H+. And we showed a double-headed curly arrow moving from the bond between the nitrogen and the hydrogen onto that nitrogen element. Now we're going to do a homolysis reaction. We have a much more complicated molecule, not overwhelming, but just many more atoms, and the bonds are all now different. So I needed to specify which bond I wanted you to crack. So we're going to put 1 electron on the nitrogen and 1 electron on the oxygen. So we show curly arrows moving those 1 electrons to each of those respective elements. But we're going to use a fishhook arrow to indicate the movement of only 1 electron. That's going to give us these 2 species. And if you draw that, you are done. You've separated the elements to show that the bond was broken. Everything else that they were attached to went along for the ride and did not dissociate away from the molecule. But the 2 new fragments have now split apart, and we should show them as such as opposed to being connected. Okay, now the heterolysis reaction here, we could push the electrons in either direction. You could, maybe I'll draw both scenarios. So if we split them so that we push the electrons over to the oxygen element, then the carbon is going to be positively charged. The oxygen is going to be negatively charged. Or conversely, you could have the answer in opposite, that is the covalent bond that we must break. I'm going to push the electrons over to the carbon atom, and that would give me a carbon with a negative charge, and the oxygen then would have the positive charge. Okay, so for heterolysis reaction, there generally are 2 possibilities. Don't worry too much if you didn't follow what I said about electronegativity, where the lone pair of electrons wants to end up on the more electronegative element. That'll come in time. What we want to do now is draw arrows correctly and be able to draw the resulting products and make sure the arrows correspond to the correct event, whether it's heterolysis or homolysis. So hopefully you appreciated this opportunity to practice homolysis and heterolysis reactions. It's these bond breaking events that once we master these, we can start to get a grasp for bond making events, which were actually exactly the opposite of what we just did. So the homolysis and heterolysis reactions could actually work in reverse with similar types of arrows just moving in opposite directions, and that would give rise to our products of bond formation. Okay, anyway, I will end the lecture there.